Hello all, my name is Anirudh. I'm a PhD student at Robert Bosch Center for Cyber Physical Systems. This is the video presentation of our paper OGP-Net, Optical Guidance Meets Pixel-Level Contrastive Distillation. To improve the robot, to improve the robotic perception in adverse weather conditions and low illumination settings, using only RGB images is not sufficient since its semantic information is compromised. Using IR sensors can be an alternative. However, as observed in this video, IR sensors capture significantly less semantic information compared to its RGB counterpart. Hence, the motivation is to develop deep multimodal fusion techniques to combine the strengths of both modalities. The goal of multimodal systems is to observe the same object from different imaging modalities, in our case RGB-IR. Low frequencies generally represent modality shared information and high frequencies represent modality specific information. The goal of multimodal systems is to leverage correlations between modality shared and modality specific features in the feature space. Fusion techniques can be classified into multimodal image fusion and multimodal feature level fusion techniques. Multimodal image fusion techniques would generate a fused image using both RGB and IR images. Once this fused image is generated, models are trained for their respective downstream task. Due to a lack of supervision while training the model using the fused image, these models don't learn the modality shared and modality specific information. This is the main drawback of multimodal image fusion techniques. Multimodal feature level techniques can then be classified into feature level fusion and knowledge distillation techniques. The main issue with knowledge distillation techniques is that when there is a significant domain gap directly aligning the features may cause a negative transfer, may break the feature alignment, and hence may cause a performance drop. Feature level fusion techniques such as aggregation based or alignment techniques can be used. In aggregation based techniques, each modality has its specific encoder. The main drawback of aggregation based techniques is that due to the requirement of having a separate encoder for each modality, this increases the parameter count drastically. Hence, this can lead to overfitting issues. Alignment based techniques such as channel exchange network have been proposed. However, these techniques generally don't perform well in missing modality scenarios since exchanging the channel may disturb the discriminability of these fused features. We formulate a problem where a segmentation model F is trained using RGB and IR images to generate a segmentation mask S. During training, both RGB IR image pairs are available. However, during inference, we have two separate scenarios. For multimodal settings, both RGB IR images are available. However, during missing modality scenarios, only the IR images are available. The main contributions are, we propose optically guided pixel-level contrastive learning network OGP-Net. OGP-Net has two main contributions. First is distillation with multi-view contrastive learning. DMC increases the correlation of modality shared features in the encoder of OGP-Net. DUR is proposed to decrease the correlation of modality specific features. That is, it tries to balance the modality specific features of both RGB and IR. It also introduces Gated Spectral Unit to eliminate manual tuning. Experimental evaluation shows that OGP-Net consistently outperforms state-of-the-art models for both scenarios. It effectively trains using limited RGB IR images and it achieves faster convergence. While training OGP-Net, there are two steps. Step 1 is training the baseline segmentation model on RGB images. Step 2 is training OGP-Net using both RGB-IR images while simultaneously distilling knowledge from the baseline model. During training step 1, the baseline model, which in our case is DeepLab V3, is trained only on RGB images. An auxiliary head is also used to train the encoders using downsampled labels. Segmentation loss is used to train the baseline segmentation model end-to-end, which consists of cross entropy and dice loss. Once trained, the baseline model is kept frozen. In the second step, OGP-Net is trained. In this step, OGP-Net acts as a student and undergoes pixel level knowledge distillation from the baseline model, which acts as a teacher. DMC projects the rich semantic information into a unified latent space. In this latent space, the correlation between the modality shared knowledge is increased. DUR focuses more on maintaining the modality specific representations. In DMC block, the encoders for the dual encoders for both modalities RGB and IR have shared convolution filters but have distinct batch norm filters. DMC integrates feature exchange, pixel level knowledge distillation, and multi-view contrastive learning simultaneously. In feature exchange, this mechanism dynamically exchanges channels in both the dual encoders. Feature exchange converts the unimodal features and represents them with rich multimodal representation from both modalities. Channel exchange and spatial exchange are performed across the encoders, and they are avoided in the deeper layers of the model to limit their interference with the modality-specific learning. Also, feature exchange when we integrate feature exchange in DMC, we do not use any sparsity regularization. Pixel level knowledge distillation. Since we are dealing with RGB and IR modalities which have significant domain gaps, we enforce strict constraints for pixel level alignment. Features from the last two layers of the encoders and the last layer of the decoder are compared using mean square error loss. This is highlighted by LD2. Finally, we propose the use of multi-view contrastive learning. The feature maps, as a result of feature exchange and pixel level knowledge distillation, now have rich multimodal representations of both the sensors. We term these feature maps as multi-view feature maps, MVFM, as shown as in the figure. We propose the use of contrastive learning on these MVFM. This reduces the use of additional data augmentations or explicit views. The features are projected into a separate embedding space using projection layers, and supervised contrastive learning is applied on these multi-view feature maps. Semi-hard sampling strategy is used while training using multi-view contrastive learning. In DUR strategy, we try to prioritize the modality-specific information. We use knowledge distillation where we compare the output predictions of the baseline model and the output predictions of the optical branch of OGP-Net using dist loss as proposed by Yong et al. We also integrate GSU into OGP-Net. As observed in the figure, GSU takes the output of RGB, IR and the summation of both as an input. It uses gating mechanisms and avoids manual adjustments. As observed, H and Z both are convolution layers followed by the respective activation functions. As seen in the equation, tan H is the activation functions for H, and for Z we use sigmoid activation function. Finally, SGSU is given by the equation. To train OGP-Net, the overall optimization used is LS2, which consists of segmentation loss followed by LD1, LD2, and multi-view contrastive learning loss. Experimental results are validated on 3 open source datasets on a bunch of different experimental settings. We validate the performance of OGP-Net, compare it with other state-of-the-art and baseline models on all 3 datasets for both multimodal and missing modality scenarios. As observed, OGP-Net attains the best performance with comparable model complexity to baseline model or similar complexity as baseline model. We also compare the performance of OGP-Net with state-of-the-art knowledge distillation techniques. As observed, due to significant domain gaps, state-of-the-art knowledge distillation techniques don't match the performance of the baseline IR model. We also retain the philosophy of channel exchange. We show that using sparsity constraint while using feature exchange mechanism in DMC is not an optimal approach. We qualitatively show the TSNE visualizations for both multimodal and missing modality scenarios, and we show the qualitative performance. In summary, we propose OGP-Net to simultaneously deal with multimodal and missing modality scenarios. DMC and DUR are used to maintain the correlation of low and high frequencies. OGP-Net has same or very comparable model complexity to baseline model with a much improved performance. Experimental results show OGP-Net consistently outperforms state-of-the-art models. Thank you.